we're back. Okay, sorry. So we are checking whether the cosine function is linear. So let's check the additivity. So our input is t. So we have f of t1 is equal plus f of t2. Is this equal to f of t1 plus t2? Okay, so on the left-hand side, we have cosine of omega t1 and plus cosine of omega t2. And the question is this equal to the input with the function applied? So, is there any more room? Okay, so clearly this is not equal, right? So this is going to be nonlinear. Okay, so you can check the additivity on your own, but the results are in the PowerPoint. Okay, let's try to go to our top hat to look at some. All right. So let's see, we are here. So again, the top hat will be used mainly for participation and for attendance, and that'll start after I get back. So we talked about linearity, we talked about I don't know why this doesn't work very well, but anyways. Okay, so in summary, we have a linear function, looks like the one on the left, where you have a straight line going through the origin. So you can think of like a spring law as a linear function. And a nonlinear function is basically anything else. So you can see an example here on the right. All right, so let's check your understanding. Which of the following is true regarding a system to be classified as linear according to the properties discussed? A, the system needs to satisfy only the additivity property. B, the system is considered linear if it shows numerical stability and scalability. C, a system is linear if it satisfies both additivity and homogeneity properties. Or D, a system needs to process inputs and outputs at variable rates to be considered linear. Okay, so hopefully you chose C. Oops. So C is the correct answer. All right, now which of the following scenarios correctly illustrates the violation of linear system properties? A system doubles the output when the input is doubled, but the addition of inputs does not lead to the addition of outputs. An output remains proportional to the input, and the addition of two inputs equals the addition of their respective outputs. A function where the output is the square of the input, describing both additivity and homogeneity. Or D, doubling the input results in less than double the output, but the sum of two inputs results in the sum of the outputs. So which of the following illustrates the violation of linear system properties? So the correct answer will be A. And I believe D is also correct because it doesn't satisfy the homogeneity property, but it does satisfy the additivity property. So B is actually describing a linear system, and C is talking about the square of the input, which is nonlinear, and so this is not additivity and homogeneity. All right. So how are we going to deal with nonlinearities? Because we have systems that are nonlinear inherently, and we need to have a way to deal with them. And so the way we're going to do that is by this Taylor series expansion. So you would have learned this probably in your Calculus 2 class. So as a reminder, function that is differentiable n times can be approximated with this Taylor series expansion, and this is how it looks like. So you take the first derivative, and you have that being multiplied by a finite interval, and then the second derivative multiplied by a finite interval squared, and so on and so forth. And so this describes approximately this function f of x. So we're going to use actually the first two terms of this Taylor series expansion to approximate a linear function. Okay, so the key takeaway here is that we're looking at this small area around this operating point, x bar. And in this interval, we can approximate a linear system. So this is going to be our linear approximation. So, we're eliminating the higher order terms with the x squared and whatnot, and we're just focusing on the linear terms. Okay, and it turns out that this error is going to be bounded by this function here. The second derivative of the function times the square of this interval. Okay, so let me go now to the notepad and we'll look at an example. All right, so let's consider x squared, which we know to be nonlinear, and let's approximate it as a linear function around this interval 0.8 to 1.2. So just as a reminder, it's always good to have a mental image of these functions. So this is what your x squared approximately looks like. This is 1 and 1, and then you have 2 and 4 and 3 and 9, right? So every input is going to be squared. So this is 1. So this is 1. This is 2. This is 1. And this is 4. Okay, so on and so forth. So this is what and so we're looking at a range between 0.8 and 1.2 on the x-axis. All right, so if we apply this Taylor series expansion, then this is approximately equal to the function at x bar plus the derivative of the function at x bar times this interval. So this is equal to f at x bar, so this is x bar squared, plus the first derivative is 2x bar times x minus x bar. All right, and we're told that x bar is equal to 1. So 1 squared is 1 plus 2 times 1 times x minus 1. So this is going to be our approximate f of x, 1 plus 2x minus 2, which is 2x minus 1. And this is bounded by some error term, which is going to be the max of this interval c from 0.8 to 1.2 of 2 times c minus 1 squared divided by 2. So this is, again, our x bar here. And so 2 times 1.2 minus 1, squared divided by 2 is 0.2 squared. So the error is bounded by 0.04. It's going to be less than or equal to this. So that's pretty good. So you can see for small ranges like this here, we get a pretty good bound on the error. If you increase this range to the point where now you have a much larger interval, your error is going to increase. Okay, so we really want to focus on linearizing around this small range. All right, so let me go back now. I can't figure out why this is so. Okay, so anyway, here's the take-home message. If the variables are restricted to this small region around this operating point, then a smooth nonlinear element can be approximated by a linear function. All right, so this is the takeaway. Great. So this is what we're getting in this small region here, delta f, delta x. We get this linear function that approximates this nonlinear function here. Okay, let's go back to our notepad. So now we're being asked to sketch the following function and find a linear approximation at the specified points. All right. So let's start by sketching. So we have this sinusoid function, right? Looks like this. So clearly this is not linear, right? We can just see from the sketch. So we're gonna pick a point. So we're starting with x bar equal to 0. We're gonna approximate a linear function, something like this, at this point 0. All right, so sine of x is approximately equal to sine at 0 plus the derivative of sine. So let me write down the equation again. So f of x is approximately equal to f of x bar plus the derivative at f of x bar times x minus x bar. So this we'll often call delta x, just so you know. Okay. Jeez. Perfect. There we go. So that's the equation. So we're plugging in for x bar equal to 0 to start. That's our first approximation here. So at f of x bar, it's sine of 0 plus the derivative of sine is cosine. At x bar is 0 times x minus x bar. So we get sine of 0 is 0 plus cosine of 0 is 1 times x minus x bar. So this is approximately equal to x minus x bar, which is just x in this case because x bar is 0. Okay, we can also call this delta x, so this would be equal to delta x. Okay, so you can see that f of x is equal to x. This is our linear function, which goes through the origin here. Cool, let's do our second example. So at our second example, pi over 2, if you think about where that is, so this is again your omega, and this is sine of x So, I mean, x being omega, so here. So this is your pi over 2. So now your function is going to look something like this. Okay, so what is that function? Well, let's find out. So now we're going to say sine of x is approximately equal to sine at pi over 2 plus cosine at pi over 2 times our delta x, or rather our x minus x bar. Okay, so sine at pi over 2. So remember, you draw this unit circle. This is your sine at pi over 2, that's 1. Plus cosine at pi over 2 is 0. So your function is actually a constant, right? Which makes sense based on our drawing here. It's equal to 1. Okay, for the last one, sine of x is now going to be approximately equal to sine at pi plus cosine at pi times x minus x bar. So sine at pi, so this is pi, sine is 0, cosine is negative 1, times x minus x bar. So this is equal to negative 1 delta x, or if you plug in for x bar, negative 1 times, so negative x plus pi, right? So again, if we look at where's pi, that's right here, and we approximate a line at pi, like this, you see that this is negative x, because it has a negative slope, plus pi. So it intersects the y-axis at pi. All right. Okay, so this is just what we discussed. Okay, and again, you can compute the error. We won't be so concerned with this because we'll assume that, again, that we're working in this small region, but you can see now that we have these different functions when we are approximating at these different operating points. All right, let's do one more example. And this time we're going to approximate the following function, the tangent inverse function. So this function looks like this. And so we want to approximate this at, again, different operating points. So I'm not going to go through the math on this, but you can see, okay, at the operating point x bar equals to 0, we get the tangent inverse at 0. Then you take the derivative of tangent inverse, which happens to be this 1 over 1 plus x squared times our x minus x bar. And so this is approximately equal to our x, or delta x, since inverse tangent of 0 is right here at 0. Okay, and similarly for a different operating point, you plug in for 1 now, you get pi over 4 plus 1/2 times x minus 1, or pi over 4 plus 1/2 delta x. Okay, so here's two examples of how to approximate a linear function. And so you might get different things depending on what your operating point is. So here is the general approach. We want to identify the operating point and then linearize around that operating point using that first order Taylor series expansion. So the question becomes, how do we choose the operating point? Well, we're going to talk about something called equilibrium points. And so we're going to consider the following dynamical system. So assuming that our function is evolving in time according to this equation, where d of x dt, our variable x, is evolving as a function of f, and its derivative is equal to f of x, then the operating point is exactly where this derivative is equal to 0, which means that we're going to set this function equal to 0. And this is going to give us the steady state solution because this derivative is equal to 0. And so we can linearize around this equilibrium point so that we ensure that we get this steady state point. And it's so let's look at an example of this. So let me go to the equilibrium points. So for this function, we have d of x dt is equal to 4 times x plus 1 squared. So we're going to set 4 of x plus 1 squared equal to 0, because we're setting this whole thing equal to 0, and we're going to solve for x. So x plus 1 squared, so if we divide by 4 on both sides, we get this. So this means that x is equal to -1, right? Okay, so this is going to be x star, and that's going to denote our equilibrium point. All right, now let's find for this guy. So again, we're setting this equal to 0 because we want the derivative to be 0. This gives us this equilibrium point. And so when we do this, we can factor this, so we get x minus 50 times x minus 30, and so we have equilibrium points at 30 and 50. Okay. Okay, so what best describes the significance of finding the equilibrium points in a dynamic system represented by the equation dx dt is equal to f of x? A. Determine the points where the system behavior becomes predictable and steady. B. To calculate the maximum and minimum values of the function. C. To identify the initial conditions necessary for system stability. Or D. To estimate the overall energy consumption. Excuse me. So hopefully you chose A. So the equilibrium point is going to be this point where the system behavior is reaching a steady state. So that derivative is 0. All right, so again, if we have this relationship where the derivative of x of t is equal to f of x, then we can identify the equilibrium point and linearize around it using that Taylor series expansion. All right, so we're gonna comment briefly on stable and unstable equilibrium points. So an equilibrium point is said to be stable if the system, when it's perturbed slightly, it returns back to this point or stays close to it. It's unstable if when the system is perturbed, it moves away. So let me give you an example to illustrate this. Oh, before that, I'm going to give you a question. Which statement best describes the behavior of a system at a stable equilibrium point after a slight perturbation? So A, the system returns to the equilibrium point or remains close to it. B, it moves away and diverges. C, it oscillates indefinitely without settling. D, the system immediately stabilizes without any perturbation effects. So the correct answer is actually A. All right. So here's an example of linearizing around this equilibrium point. And we're going to first start by finding the equilibrium point. So, I'm sure you have all seen people riding these one wheels around campus. And you can see that this one wheel, it looks very similar to what we call an inverted pendulum. And we can actually mathematically model an inverted pendulum with the following equations. We have the force equation and the torque equation. Okay, and so in order to find the equilibrium points, we have to first set the system at rest. And so we have to set the angular velocity to be 0, the position of the cart to be 0, the angular acceleration of the person on the one wheel to be 0, and the acceleration of the cart to be 0. Okay, so x, again, remember, is the position of the cart. Theta is the angle here from the vertical of the body of the person on the one wheel. All right, so these are the equations here, and we want to find the equilibrium points. So let me go back to our notepad here. So if we set, again, the system to be at rest, and we solve for theta and x, we should find our equilibrium points. So theta, remember, is this angle, and x is the position of this cart. And so we want to find what are x bar and what are theta bar. All right, so we plug in 0 here, 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 and we also don't want any input. So what does that leave us? Well, basically, that means that 0 is going to be equal to 0. Okay, that doesn't give us a whole lot of information about theta bar or x bar, right? So let's look at the second equation. If we plug in 0 into our acceleration, 0 angular acceleration, then what do we get? So all the second derivatives and first derivatives we've set to 0. So we have 0 plus 0 minus mgl times the sine of theta equal to 0. And so we have sine of theta is equal to 0. And so theta then must be 0 or pi, right? So this is our equilibrium point. It's either going to start at 0 or pi. So again, as a reminder, in this, the definition, the 0 is going to actually start at the vertical, and then the pi is going to be at the at the 180 degrees from it. Okay, and then what about x bar? Well, x bar can actually be anything, because we can start at any location on the horizontal here, and that will be the system is at rest. because it's still not moving, and so we want to keep the pendulum either completely upright or you know, completely fallen down here. Those are our equilibrium points. All right, so another system we can think about is yes, exactly. So here at theta equals 0, the pendulum is upright, and here the pendulum at theta equals pi, the pendulum is fallen down. Okay, we can also think about an inverted pendulum, and we can find the equilibrium points for this. So this is a simpler equation where now we're just looking at the swinging movement of this pendulum. So I don't know if you guys have seen this before. When I was growing up, we had this at the Science Museum. Very interesting. You could watch it for hours. But anyways, so for the system to be at rest, you need the angular acceleration to be equal to 0 and the input to be equal to 0. So when we plug this in, this is going to be 0, this is going to be 0, so we get negative mgl sine of theta is again equal to 0, so again, our theta star has to either be 0 or pi. And this kind of makes sense because it needs to be completely down or completely up. So here, you'll see when it's completely down, this is a stable equilibrium point, right? If you perturb it, it's going to eventually settle back down. If it's completely upright, then it's going to eventually fall back to its stable equilibrium. All right, so now we want to linearize. I'm going to skip past this. How can we linearize this guy around its equilibrium point? All right, so we found the equilibrium point. We found its stable equilibrium point, and we want to, and the inverted pendulum, this is an unstable equilibrium point. So let me go back. For the pendulum, it's defined differently. So here at 0, because we're defining our starting point to be 0, this is unstable, and at pi, this is going to be considered stable, whereas it's defined at 0 for the for the pendulum is at 0, and the pi is considered unstable. So anyway, they're just different definitions of the same thing. All right, so let me go now we're going to linearize this thing. All right, so as a reminder, f of x is approximately equal to f of x bar plus d derivative of f of x bar times x minus x bar. All right, so we need to first identify our nonlinear terms. So we know that cosine is a nonlinear term and sine is a nonlinear term. So we have them in a couple different places. So we're going to linearize the cosine and the sine. The other terms are actually just derivatives, and those are linear inherently. All right. So let's linearize cosine around its equilibrium point. Okay, so this is cosine of theta bar plus the derivative of cosine of theta bar times theta minus theta bar. Okay, so cosine of 0 plus the derivative of cosine is negative sine, right? At 0 times theta minus theta bar. Okay, so cosine of 0, cosine of 0 is 1. Sine of 0 is 0. So this is going to give us 1. Okay, I forgot one thing here. So we linearized cosine, but actually this term is a squared term. And so this whole term is actually nonlinear. And so we're going to actually linearize this theta squared sine of theta. So this is equal to theta bar squared sine of theta bar plus 2 times, so the derivative of this, we actually need the chain rule. So this is 2 times theta double dot sine of theta plus cosine of theta bar. This is the derivative with applying the chain rule all times. Oh, I'm sorry. I forgot one term. Theta bar squared times theta minus theta bar. Okay. So what's interesting is, remember we fixed the derivative terms to be 0. So all of these are going to be 0. So our function is 0. That's the linearized function. So when we plug these in, oh, and we can also linearize sine. We've done that before. So when we plug these in, basically now, the linear version of this is going to be our 2 masses times the second derivative of the position of the cart plus m times L theta double dot times our linearized version of cosine is 1 minus ml times the linearized version of this guy is actually 0. So we can just totally eliminate this term, and this is equal to our u of t. So this is the linearized version of our nonlinear force balance equation. Okay, and we can apply the same thing for the torque balance equation. And so again, plugging in for the cosine here, so we get ml x double dot times 1 plus ml squared. So this is a parameter. So this is not one of our this is not a function of time, so it's not considered a nonlinear function. So anyway, that's why we ignore this, because it's a parameter. It's actually just like a scalar value times the second derivative of the angle minus mg, and then it turns out, okay, we need to linearize sine. So let's linearize sine. So sine of theta bar plus the derivative of sine at theta bar times theta minus theta bar. So sine at our equilibrium point 0. So sine of 0, plus the derivative of sine is cosine of 0 times theta minus theta bar. So this is Sine of 0 is 0, plus cosine of 0 is 1, times theta minus theta bar. So this is going to be theta, because theta bar is against 0. So sine of theta for at theta bar is equal to 0. Is equal to theta, sorry. So we plug in theta here, mgl times theta equals 0. So again, this is our linearized version for the inverted pendulum. Okay, so we can do the same thing for our pendulum, and I'm gonna go ahead and skip that because it's here in the slides. So if you linearize around this point, then you'll see something very similar where we linearize cosine, we linearize sine, and we get this equation at the end of the day. All right, the problem I want to get to is the following. This is one of the practice problems for the exam, and I just want to go over it now. So you're given a mechanical system with a nonlinear spring. So this is a mass, and this is a damper, and this is a spring, and this mass will oscillate when you apply a force to it. And so we have this nonlinear spring, and we're asked to find the transfer function of the position of the mass with respect to the input force. And there are, assuming that we have some small excursions around the force at time, for f of t is equal to 1. Right, and we're told that the spring is defined by the following nonlinear function, where x of s of t is the spring displacement. All right, so how to begin? So let me go to our notepad here. So we start by writing the sum of the forces. And actually, really, we should start by writing a free body diagram. So we have a force acting in this direction, and then we have two opposing forces. One is by the spring force, the nonlinear spring, and one is by the damping force, which is a linear. Okay, so if we write the sum of the forces now, where this is our positive direction, we have f of t minus fs of t minus fd of t is equal to our mass times acceleration, which is the second derivative of the position, right? Okay, so we know this. This is equal to the damping coefficient times the first derivative of the position. So this is f of t, our input, minus f of s minus dx dot is equal to mx double dot. Okay, so how do we get the force from the nonlinear spring? Well, we're told that x, the position of the nonlinear spring, is equal to 1 minus e to the negative f of st. So we really need to solve for f of st, so then we can linearize this guy, right? Okay, so how are we going to do that? So x of st minus 1 is equal to negative e to the negative f of st. If we multiply by negative 1 on both sides, we get 1 minus x of st is equal to e to the negative f of st. If we take the logarithm of both sides, we get the natural log of 1 minus x of st is equal to negative f of st. and then we take the divide by -1 on both sides, we're left with f of st is equal to negative log of 1 minus x of st. Okay, so this is the force on the nonlinear spring. So if we rewrite this here, we get, let me move this a little bit. So this is the function we just found. Negative log of 1 minus x of st. Alright, so if we plug this in, we get f of t plus natural log of 1 minus x of st minus the damping force is equal to mx double dot. Alright. So the question now is, what is this x of st? Well, the position of the spring is coupled to the position of the mass, so really x of st is equal to x of t. Okay, so we can replace this, so we have the natural log of 1 minus x minus d times x dot is equal to mx double dot. All right, so now we are ready to linearize this guy. Okay, so it took a little bit to get there, right? We had to find our free body diagram. We had to find the sum of the forces. We had to solve for this f of s. We had to replace x of s with x, and now we're ready to linearize. So let's assume that first let's move all the x terms to one side. So we have our input is equal to mx double dot minus the natural log of 1 minus x plus dx dot. So we want to linearize this guy. All right. So let's call this g of x. This is equal to our natural log of 1 minus x, and we want to linearize g of x. So g of x is approximately equal to g of x bar plus the derivative of g at x bar times our interval. All right. So this is equal to the natural log of 1 minus x bar plus the derivative, which is 1 over 1 minus x bar times x minus x bar. So you may not remember this derivative, but the natural log is 1 over 1 minus x bar times the, and it's a positive because we multiply by the derivative of this guy, which is -1. Okay, so the only thing we have to figure out then is, what is x bar? Well, if we go back to the problem, we are told that we're going to have some small excursions around the input force f of t. So really what this means is, if we think about linearizing f of, we don't need to linearize f of t really, but f is going to be equal to f bar plus some perturbation around f. And we're told that f bar is equal to 1. So f is actually 1 plus this delta f. And x is equal to x bar plus some perturbation around x. Okay, so we can start to replace these terms by their delta terms. All right, so what do I mean exactly? Well, we have m times the second derivative of x minus our nonlinear term. So this is the natural log of 1 minus x bar plus 1 over 1 minus x bar times delta x plus d times the derivative of x is equal to f. And f is equal to this guy here. 1 plus small perturbations around f. Okay, so really we need to replace this x and this x with our x bar and delta x so we can solve for that delta x. So now we have the second derivative of x bar plus delta x with respect to time minus our linearized version of the nonlinear spring plus d times the derivative of x bar plus delta x. And this is 1 plus delta f. Okay, so the derivative of x bar, where, remember, x bar is a constant. So the derivative of a constant is 0. So really, all we're left with is the derivative of this delta x. Okay, so I'm rewriting this here. Okay, and similarly, the derivative of a constant is 0, so we're left with the derivative of delta x dt is equal to 1 plus delta f. All right, so let's notice that we have this delta f term, delta x term, delta x term, delta x term, and then we have this delta f term. So these are our variables. But here and here we have constants. So what we can do is we can actually equate these constants. So 1 minus negative log of 1 minus x bar is going to be equal to 1. And now we're ready to solve for our equilibrium point. Okay, so this was a little bit convoluted, but I think it's good to kind of think about, okay, we have some operating point and we have these small perturbations around it. Similarly with our input, how can we find this equilibrium point knowing all this? All right, so when we solve for this, I'm going to skip some of the mathematical details, but basically now x bar is equal to 1 minus e to the negative 1. So we can plug this in for x bar here and here, and then we will find that we are left with the following. Okay, so we have m second derivative of delta x dt negative log of 1 minus 1 minus e to the negative 1 plus 1 over 1 minus 1 minus e to the negative 1 delta x plus d delta x, oh, sorry, there's a derivative term, plus d derivative of delta x dt equals 1 plus delta f. Okay. So 1 minus 1 is 0, and then the natural log of e to the negative 1 is 1. Okay, so we have this, and then we have this term. So again, this is 1 divided by 1. No, sorry, this is 1 divided by 1 minus 1 is 0, 1, and then negative. So this is 1 divided by e to the negative 1, which is really just e, right? Okay, so we have the following. And I forgot this little squared here. So this is minus 1 plus e delta x plus d derivative of delta x dt is equal to 1 plus delta f. So what's neat now is actually, sorry, this should be a plus because we have a plus here. This one and this one will cancel. So now our final differential equation here is the second derivative of this perturbation around the mass plus e times this perturbation plus the damping coefficient times the derivative of this perturbation is equal to the perturbation around the input force. And so now we can actually take the Laplace transform of this. So we get m times the, m times s squared delta x of s plus e delta x of s plus d s delta x of s is equal to delta f of s. And so if we find the transfer function of the perturbation around x with respect to the perturbation around f, I'm skipping some steps, but if you factor and then divide, you'll get 1 divided by ms squared plus e plus ds. Okay, so this is your final transfer function for the perturbation around the position of the mass with respect to the perturbation around the input force in your mass spring damper system with a nonlinear spring. All right, so you can go through the steps again and kind of see where we got that from, but the key point is that you're going to need to linearize any nonlinear terms that appear in your differential equation, okay? And so what we see is that when we start with physical reality and we get a nonlinear differential equation, we have to first linearize before we can take the Laplace transform. And then we're going to use that Laplace transform to actually analyze our system. Okay, so let's answer the following question. Which steps correctly represent the transition from modeling a real-world mechanical system to its mathematical representation? Is it A, linearizing nonlinear differential equations and then applying the Laplace transform? Is it B, applying the Fourier transform directly on nonlinear equations? Is it C, modeling reality into different linear differential equations, then applying the Laplace transform? Or D, direct transformation of nonlinear systems to linear systems without intermediate steps? Well, it definitely can't be D. You could model physical reality in as linear differential equations, but usually we find that many systems are nonlinear, and then we linearize. So we're going to have to go with A. Okay, great. Think about what today's class did to build on what you've learned in previous classes, especially with respect to your calculus class, maybe even a signals and systems class. And if there's something else, I'd be curious to know. And what concepts or topics did you find most challenging to understand? So, as a reminder, homework 2 is going to be due on Tuesday, September 9th. And next week, you can find me in my office on Monday and Wednesday. Okay, the next lecture is going to focus on the transfer function of linear systems. So, see you then.